Hello, my name is Ingrid Befring Hage and I'm a master's student at NTNU in Trondheim, Norway. I'm now going to present the work that I did in the fall of 2019, which concerns the design of a contra-rotating booster pump. The background for this project is the increased interest in renewable energy sources, such as wind and solar power. However, these sources are very variable in their production of energy due to them being entirely reliant on weather conditions. They produce energy when the conditions are right and not necessarily when the demand for energy is high. This causes for an unstable electricity grid, which needs to be solved. One way of doing that is by storing energy, for example with pumped hydroelectric storage or PHS. PHS can be used in hydropower plants that are located in between two reservoirs, one lower and one upper, where you can pump water from the lower reservoir when the energy demand is low up to the upper reservoir, and then use this water later on when the energy demand is higher again. This can also be used in existing hydropower plants by retrofitting it for PHS. You can just exchange the turbine with a reversible pump turbine or RPT. And in that way you can use a lot of the existing construction surrounding the turbine, such as the waterways. The biggest problem with this method of using PHS is cavitation, because when the RPT is located in the old turbine location, it will not be submerged enough when the reversible pump turbine is in pumping mode. This means that the static pressure is lower than the vapor pressure and causes bubbles, which can be fatal to the operation. One way of solving this problem with the cavitation is by placing a booster pump in front of the RPT when it's in pumping mode. So that means that it will be placed between the draft tube and the lower reservoir. This will increase the pressure at the inlet of the RPT in pumping mode, which of course will reduce the cavitation and also provide extra pressure head for the pumping process itself. This booster pump needs to accommodate for the needs of the RPT, meaning that the swirl of the outlet flow from the booster pump can be little or non-existent. This can be solved by using a contra-rotating axial pump as a booster pump due to the rear rotor cancelling out the swirl from the front rotor. Also, when the RPT is in turbine mode, this booster pump will be in the outlet flow, which can affect how the RPT is working. Therefore, the concept of placing the motor in the periphery of the machine instead of having a shaft-driven machine is going to be investigated, as this would cause for an easier way to lift the booster pump up of the flow instead of it being constantly in the outlet flow of the turbine. I will now present a literature review of existing contra-rotating machinery and shaftless machinery to investigate the previously mentioned ideas for this booster pump. This information will later on be used when deciding on a design philosophy in a later phase of this project. I will now talk about contra-rotating machinery, and you can see a typical machine in the picture. It has two rotors operating in the opposite direction of each other, and it is mostly used in marine propulsion and in the contra-rotating propellers. It has several advantages, such as lower blade loading, higher efficiencies, and the cancelling of swirl from the front rotor. I will now present two studies performed on contra-rotating axial pumps. The first one is for axial pumps for higher specific speeds, because they found that axial pumps with single rotors had deteriorating performances for higher specific speeds, and wanted to see if the contra-rotating type could solve this. The study had the front and rear rotor operate at the same rotational speed, and they found that cavitation occurred in the tip region of the rear rotor, suggesting that there was a pressure drop between the front and rear rotor. And they also found disturbances in the velocity fields, suggesting blade rose interaction. This can cause repetitive stress that again leads to an unsafe and unreliable operation. This study suggests that rotational speed optimization could solve both of these problems, meaning that you would have the front and rear rotor operate at different rotational speeds. Another study was performed on the internal flow of the contra-rotating axial pump, and this was done to see why they previously had unsatisfactory performances in an axial or contra-rotating axial pump. And they found that there were strong secondary flows and corner separations occurring in the rear rotor, which blocked the inlets of the rear rotor, turning the flow towards the tip. And in addition, they found tip leakage vortices from the leading edge, which again was assumed to travel into the blade passage and then cause another blockage. And the unsatisfactory performances was assumed to be due to tip leakage vortices. And now over to shaftless machinery. There are different kinds of this type of machinery, such as some tidal turbines. However, Straflo turbine, for example, there is only one successful installation of it, and Open Hydro, which produced similar turbines, was liquidated in 2018. A more well-used concept is the rim-driven thrusters, or RDTs, that can be found in marine propulsion, and you can see it in the picture here. This arrangement makes for a more easy and flexible installing of the machine, which is the main advantage for this project. I will now talk about two studies that have been done on RDTs. The first one was a numerical simulation of different blade geometries for them for the same diameter. In this case, the tip will still be in the periphery of the machine, while the root will still be in the middle, where the hub would be. This study found that tip leakage vortices did not present themselves in 2 of the cases. However, root vortices did appear. And this study suggests that both tip leakage vortices and root vortices can be controlled with the right blade loading distribution. Another study, also a numerical study, investigated the RDT in uniform and non-uniform flow, and they found that sheath cavitation occurs for both cases on the suction side of the blade, while for the uniform flow there is no tip leakage vortices. I will now discuss some of the findings that I've done in this project, starting with the contra-rotating type. This of course has several advantages that I've already mentioned, such as higher efficiency and reduced blade loading. And most importantly for this project is the cancelling of the swirl from the front rotor, meaning that the booster pump would have a uniform axial flow in the outlet, and this is exactly what is needed. However, the cavitation in the tip region of the rear rotor that was found in one of the studies on contra-rotating axial pumps is something that needs to be fixed. But there is reason to believe that introducing the rim-driven concept to the contra-rotating concept can remove this problem, as the studies on RDTs showed a reduction in tip leakage vortices. However, this causes for another problem, that is root vortices occurring, which would also be necessary to look into. But as mentioned previously, this was suggested that could be solved by having the right blade loading distribution. Also, by having the rim-driven concept introduced, there would be an easier way to lift the pump out of the flow when the RPT is in turbine mode, which is of course very beneficial for this project. The blade rose interaction between the front and rear rotor must also be addressed. As mentioned, rotational speed optimization was suggested to solve this problem, but also axial distance between the rotor can solve this. A study has shown that the front rotor showed improvements by having a larger axial distance, and that the rear rotor did not. But this is something that will be investigated further in the next phase of this project. The next step in this project is to decide on the design philosophy that is to be used, and find out how to combine the contra-rotating machinery with the rim-driven concept in a suitable way. I will also have to do numerical simulations to evaluate the performances of this design and to find out if it's at all suitable for the use in a PHS facility. This has been my presentation, and thank you so much for your attention.